Good morning, I'm Paola Murgia, Marketing Events Coordinator at Unmeca International. Let me introduce you this webinar on VNoise Aeroacoustic applications, where Giorgio Ferrante, Engineer and Product Manager for Acoustics, will introduce you the main feature of VNoise and the benefits achievable by its application. I take this opportunity to remind you that you're able to ask questions during the webinar, either through the question section or the chat. We are taking all the questions and answering by the end of the presentation, and we are also available to send you further information after the webinar if necessary. The presentation will be recorded, and if the recording goes well, we will upload the registration in the FTP account. And we will also include a PDF version of the presentation that you will be able to download after the webinar. You will receive an email including login and password to the FTP account, and you can also write us to webinars@numeca.com. So the webinar is going to start.
So good morning, good afternoon to everybody, also from my side, and we will start this webinar on VNoise. The webinar will be focused on the applications of VNoise in the aeroacoustics, and so it's VNoise, as you probably already know, it's a full integrated CFD suite that can be used for acoustic simulations in vibroacoustics and in aeroacoustics. You can perform with VNoise from a wide range coupled vibroacoustic simulations to simple pre-designed calculations. So it's a tool that can be successfully used for from the preliminary phase of the design up to the detailed phase of the design. And it allows to perform also large-scale analysis of complex problems. And you can see here in this box a sketch showing the different modules that are implemented in VNoise. The main modules are the BM module and the FEM module that are used for to compute the sound propagation. And then there are other modules that allows to perform, to study, to simulate sound radiation, and that is this module in particular, that is the Fox-Williams-Hawking module. And there is also a module that is called the flow noise that allows to reconstruct the acoustic source. Typically, the acoustic source for an acoustic analysis in VNoise has to be computed through a CFD solver, so a CFD software external to VNoise. For this reason, VNoise provides a user interface very powerful that allows to integrate very well the software to any CFD solver that you may have. In particular, the flow noise modules allows to work with the run simulations, so you can import directly a run simulation in VNoise and then reconstruct part of the acoustic source through this module. So these are the main modules that are present in VNoise, and the focus of this presentation will be to show some applications, some practical applications of the software. And for this reason, the presentation will be split in two parts. So in the first part, you will have some examples on how to apply VNoise to turbo machinery, in particular to simulate tonal noise. And two cases are considered: an air conditioning fan and a rotating propeller. In the second part of the presentation, instead, I will show you how to use VNoise to model broadband noise generated by adapted valve. I want to underline that this webinar is focused on practical applications. For a more detailed description of at a theoretical level of the modules implemented in VNoise, I remind you that this information are included in the previous webinar that was held by Numeca some months ago. Okay, so we can start with the first part, so turbo machinery application. as you may know, the main noise generated by turbo machinery is of tonal noise generated by steady flows, and this is so a deterministic noise type. And with regard to an image, to a configuration like this one, we know that the main noise comes from the rotor blade passing frequencies by the shock related to the blade tips when they rotate at a supersonic speed, by the rotor-stator interaction that is very important to generate tones, and by inflow distortion tones as well. If you make a measurement of this type of noise, you will have a spectrum like this one. So you see that the tonal component here is very pronounced. So this example of application is focused on the computation of the noise at the BPF and at the harmonics, so tonal noise. For this purpose, in VNoise we can use several modules that are this one, so the CFD integration module. We can apply a finite element modeling method or a boundary element method to compute the sound propagation. In case of rotating propeller, I will show you also an example on how to apply the Fuchs-Williams-Hawking methods. Okay, so the first case that I want to share with you and present to you is the simulation of a ducted fan. In this case, we have a fan that is ducted here, and the goal of the simulation is to compute the noise generated by the fan and radiated outside from the intake. So the rotor is very small, is 0.3 meters of diameter. We have 6 blades, 5 upstream guide vanes, and the simulation results are sampled over this microphone array that is located in front of the intake in which the fan is enclosed, and the results are then compared to measurements performed by placing here microphones. So the computational approach will be first to compute the acoustic source, so to characterize the acoustic source, and this is, we know that the source is tonal, so the source in which we are interested is tonal, and for this reason we can perform a CFD simulation to extract the acoustic pressure over the blades, and for this reason we have adopted a method, the NLH method, so the nonlinear harmonic method implemented in fine turbo. After this, once the source is computed, we then have to work with VNoise to compute the noise propagation. And in this case, the mean flow in the duct is sufficiently uniform, is low speed because this is an air conditioning fan, and it is sufficiently uniform to allow the application of a boundary element method. So for this reason, we have to generate a BEM, so acoustic mesh, and then the mesh has to be generated and imported in VNoise. Then once we have the acoustic mesh imported in VNoise, we have to import the NLH solution, and the solution will be projected onto the acoustic mesh, and this projection will be used as a boundary condition to model the source in VNoise. Then we perform the sound propagation in the duct and the radiation outside of the duct towards the free field by using a multi-domain boundary element method analysis. And then at the last step is to post-process the acoustic results and compare the results with the measurements. So this is the sequence of our computation. We will now go through each of these steps, showing some images and some of the results obtained. So the first step is the NLH simulation, as you can see here. Typically, NLH is in NLH you have two different meshes. You have a rotating mesh modeling the blade, enclosing the blade, and a fixed mesh enclosing the stator vane. It is sufficient to model just one flow passage in NLH, so just one passage of the blade over the vein. In this case, it's represented the acoustic pressure computed by VNoise, by NLH at the second harmonic, and you can see here the results. So the results are, in this case here, we see the interface, and you have the plot of the pressure expressed in Pascal. In this case, NLH was used to compute the 3 harmonics. The mesh was realized in AutoGrid, and you can see here the sites of the mesh used, and the computational time was very fast, considering that in 1 hour and a half on 24 cores we got a solution up to 3 harmonics. So this method is very powerful to compute the tonal source, tonal acoustic source, that can be then input in VNoise. The second step is in VNoise to create an acoustic mesh, and the acoustic mesh in this case is this one on the left. You see that the acoustic mesh starts with an inlet, this one, and then it contains the hub, the stator vanes, and the duct. The acoustic mesh is generated for this geometry in express hybrid. It is an unstructured grid generator, and it can be used successfully for the generation of acoustic meshes for VNoise. It has to be reminded that the sizing of the elements depends on the frequency, so we need to have at least 6 notes per wavelength. On the right side, the right-hand side here, you see that the mesh is closed with a cap represented in violet. This is because we are using, this is a BEM mesh. The BEM mesh has just to reproduce the surface, the solid surfaces of the object, but it has to be closed. So we need to close the computational domain with a cap like this, that is a part of a BEM mesh. And this mesh then will be defined as a permeable surface to allow the sound to radiate in the far field. So we can then perform the step necessary to import the NLH solution in VNoise. As you can see here, once the acoustic mesh is imported in VNoise, VNoise also imports the NLH solution. That means the NLH mesh plus the NLH solution. The meshes are overlapped, as you can see here, and on this plane, that is the plane, the inlet surface plane, the solution of NLH is projected directly onto the acoustic mesh. In this case, we are using the NLH solution, but this process can be applied to any solution that you may have obtained with your own CFD code. The result of this importing is represented here. So on the inlet surface, you see the solution, the acoustic field. This is a typical acoustic field at a given frequency, imported. For this reason, VNoise offers this import mask, in which it is possible to define whether, if I want to import the solution on a rotating frame or on a fixed frame, and if I need to generate time histories from frequency data, or the opposite, so or frequency data. And it is possible to import, if I want to model, for example, a fan, like in this case, just one blade. So the solution is computed over one blade. VNoise will automatically rotate the solution and create the full 360-degree acoustic solution on all the rotor. So once we have the solution, imported the solution, we have now to set up the VNoise model for the computation of propagation. In this case, as I said before, we are using a BEM model. It means that this is a sketch. You can see here a sketch of a section of the duct. We have imported the NLH solution on the inlet, And then on these solid surfaces, instead, we will define a boundary condition that tells to the BM solver that these surfaces are rigid, so the sound is reflected by these surfaces. And then we have, as I showed before, we have also to create a permeable mesh over the outlet to close the computational domain, and it is represented here. So we have a radiation surface, that is this one, that practically it is this mesh that will be will close the duct. And also in between the two meshes, so the external mesh and the internal mesh, we need to define a condition that ensures the continuity of field variables. So it means that here we define an interface boundary condition that allows the waves, as you can see here, the acoustic waves, to cross this surface. It is another important aspect to be considered is that when you apply BM method, you work with panels, so with a surface mesh, and it is fundamental that the normals of each panel are pointing inside the computational domain. So as you can see here, VNoise allows a very easily to verify and to exchange, if necessary, the direction of the normals. And here are represented the normals of the duct. Here are represented the normals of the cap closing the computational domain. As said before, we need to have a radiation mesh. The radiation mesh is the green one, and it is a mesh coincident with this red one, so sharing the same nodes but with different panels. And the normals of this panel of these panels are pointing clearly outside, so towards the computational domain that for this mesh is the external space. In VNoise there are masks like this that allow you to define the interface boundary condition, for example, from a closed computational domain to a radiation computational domain. Here you can link the pressure and the acoustic pressure and the acoustic velocity on this green mesh to the acoustic pressure and acoustic velocity of the inner part. So by defining, for example, this coefficient, you can allow the propagation of waves across this surface. So this is a powerful mask that allows to create the model rapidly in VNoise. Once you have set up your model, you can start your analysis, and you will obtain the radiated acoustic field over the microphones defined in VNoise. The microphones are located here outside, and what you can do typically in VNoise, you can visualize the results in terms, as represented here, in terms of sound pressure level, so in decibels. This is the map of over this microphone of the sound pressure level at 800 Hz. You can see the comparison with the experimental results obtained. And here on the right side you can see an animation of that VNoise can provide. So you can visualize the acoustic waves at a given frequency radiating from the intake. It depends where you put your microphones. You can also have values expressed from Pascal to decibels, with a narrow band spectrum up to the 1/3 octave band spectrum. You can obtain also computation of the radiated power or averaged values over a given surface, like the average impedance or the average intensity and so on. So this is a first application showing how to model a fan for ventilating systems. The second application that I want to present is the application to the simulation of noise generated by a rotor of a propeller. Here we are considering a contra-rotating open rotor, but we will apply the simulation of VNoise just to compute the noise generated and radiated by one of the two rotors, so by this one. the case is this one, is shown here. We have a rotor of 0.6 meters of diameter, and that is this one. And we have 10 blades of the rotor, and 12 are the blades instead of the contra-rotating rotor. This is the rotational speed, and the goal of this simulation is to map the noise radiated over this spherical microphone array. The approach will be to perform again an NLH simulation, because the main noise that we want to study here is tonal. And as said before, to simplify the demonstration of this application, I have just considered one of the two rotors. So we are studying the noise coming from one of the two rotors. Then what we have to do is, we start from NLH simulation. In NLH we model just one blade passage. So we have in VNoise to reconstruct the 10 rotor blades, and I will show you how to do later. And after this step, we can import the NLH solution in VNoise directly and project the results directly onto the surface mesh. NLH, as you know, provides harmonics, so the data obtained are expressed in the frequency domain, but VNoise can transform this data in the time domain to reconstruct the time history. And this is necessary because we are then applying the Fox-Williams-Hawking method that needs as an input a time history. So this is the sequence of the step that we are adopting. Here we can see an example, so a sample of the results provided by NLH. So on a given blade, we have at a given harmonic, in this case it's the second harmonic, we have the acoustic pressure. So you can see here the real part and the imaginary part, the distribution. These results are then used by VNoise. Here you can see that the computational mesh in NLH encloses model just one blade, one blade-to-blade passage. For this reason, VNoise in VNoise you can import this mesh, that is a volume mesh, and you can extract in VNoise directly the skin of the free surfaces of this mesh, creating a surface mesh made by panels. Then these panels can be rotated, this mesh for each blade can be rotated easily in order to create at the end a 10 blade surface that is represented here. So this will be, in this pre-processing made by VNoise, you can extract from a CFD mesh, you can extract your acoustic mesh that needs to be, in this case, a surface mesh that can be used for the Fox-Williams-Hawking propagation analysis. What we can see is here is again the import mask that allows easily to, once you have the acoustic mesh, allows to take as input the CFD solution, generate time histories. In this case we are generating time histories in a rotating frame because we want to have at each node of this mesh to have the time history of the fluctuating variables, and the frame here is rotating at a given speed. So we can import the solution, and you can see here at a given time step an example of the acoustic pressure distributed over the blades. And after that, it is possible to launch the Fox-Williams-Hawking radiation analysis. This analysis can be controlled by this mask. In this mask you can see, for example, the rotational speed indicated here. You can define the velocity. You can define the rotational axis. So you can define all the kinematic of your rotor here. Then you have a mask where you can include the fluid parameters, typically the sound speed and the density. And then you can select the different types of formulations. In this case, we are using the formulations of Fox-Williams-Hawking type 1A. And then you define also the maximum frequency for which you want to reconstruct the results, because Fox-Williams-Hawking provides at the end time history, and then this time history is Fourier transform to get the data that you need at the different frequencies. Here, typically, this analysis is made for a period long at least as one rotation of the rotor. And another important parameter is this one that represents the unsteady load period, so the duration of the CFD simulation. This duration of the CFD simulation can be smaller than the calculation period, than the rotational period of the rotor, as in this case. Here it is in particular is 1 over 24 times smaller. This is due to the fact that on a blade of one rotor during a rotation, the loads, the acoustic loads changes 24 times due to the interference with the second rotor that is contra-rotating. Here, at the end, you get the results expressed in frequency. This is a 1000 Hertz frequency, and you see an image showing the acoustic pressure over the microphone's arrays. So here you can get also the directivity with respect to the sound radiated with respect to the observer. And now I will enter in the second part of this presentation, in which from the computation of tonal noise we switch to computation of broadband noise. And this is typical noise that is generated by turbulence on surfaces, like over wings or wherever you have a solid body embedded in a flow. So the sound here is generated by unsteady velocities due to the turbulence, and typically you have this happens in a boundary layer or in a turbulent wake. What you can see here is that in the main modules that we are using in VNoise for this analysis are the CFD integration, the flow noise modules as well, and for computational propagation, again, finite element or boundary element methods. As said before, all the details on these modules can be found in the VNoise introduction webinar made in July. So this case is a ducted valve that you can see here. So there is a duct and with a valve enclosed in the duct. The valve is open at 45 degrees. So there is a generation of turbulence here and the noise. And then the sound is propagated along the duct, and it's radiated outside. When the sound goes outside, it is measured by these microphones. So the goal of the simulation is to compare the results calculated at these microphones with the measurements made. The step of the simulation are to perform, first of all, as the sound here is broadband, typically broadband, the first step is to perform a run simulation that provides time averaged information on the flow field. Then the run solution is imported in VNoise, and it is on the top of this solution. It is applied the stochastic noise generation reconstruction model embedded in VNoise. That is a powerful module, powerful algorithm that allows to reconstruct the turbulence from steady-state results. This avoids to perform complex and time-expensive LES simulations, and provides a stochastic approach to the reconstruction of the noise from turbulence. After that, once you have the turbulent velocities reconstructed in each CFD cell, VNoise calculates the light hill stress tensor distribution on each cell, and then through the light hill analogy, the sound is then propagated in the free field in particular over the surfaces that are represented in this case by the duct and by the valve. It is possible then to obtain the incident acoustic field on these surfaces. After that, a BM or FEM computation is then performed to compute the reflected acoustic field. The sum of the incident and of the reflected acoustic field provides the full acoustic field. So now we will see some all these steps one by one. So first of all, this is our duct with the valve. The flow is coming from the right to left side. There is turbulence generated around the valve, so we can first of all subdivide the computational domain in 3 closed domains. 2 are used for the propagation, domain 1 and 3, and this domain 2 instead is used for the computation of the source. So the first step is to perform a CFD analysis. You have here a CFD mesh that provides the Sirras analysis provides static pressure values, velocity vectors, velocity streams line, but in particular turbulent kinetic energy and the dissipation. And these parameters are used then to identify the acoustic sources, where they are located and what is their intensity. So based on the turbulent kinetic energy and on the dissipation level, the sound sources are reconstructed. VNoise allows automatically to extract the source, so to from all the CFD domain to isolate a subdomain containing the relevant turbulent kinetic energy. So the user adjusts to define the minimum value of the turbulence, and the VNoise will extract all the solid elements containing a turbulent kinetic energy higher than that value. After that, you can see here we have to define the computational model and the boundary conditions. So we have a pre-domain that is a buffer region where the waves can, where the flow and the waves can start to travel in this direction. A source domain where we have a generation of sound. A post domain that is used for the propagation. And then as the duct is open, we have to create a fourth domain that is an external domain. So as said before, this is a multi-domain boundary element method computational analysis in which there are 3 closed domains and 1 external domain used for radiation. All these domains are coupled through these interfaces that are defined in VNoise, and that allows the continuity of the propagation of the waves. The acoustic mesh can be FEM mesh, so a volume mesh, or as in this case a boundary element mesh that requires just to mesh the surfaces. So these surfaces of the duct, also including the valve surface, so to compute the scattering provided by this valve. Then once we have the acoustic source reconstructed in the internal domain, in the domain number 2, VNoise will provide the incident acoustic field on the boundary of the duct here and on the valve. So all the acoustic sources obtained from the CFD analysis and by the VNoise in this computational domain are radiated to get the incident acoustic field on the green surfaces and as well on the valve. So once you have the incident acoustic field here, you can then in the next step use this incident field as a boundary condition to start a propagation analysis. So you will add also the other 2 computational domain, and the boundary element analysis will be performed coupling together all these domains. So the sound will be generated from the valve, radiated on the right-hand side and on the left-hand side here. And once the waves arrive at the end of the duct, they can be radiated in the far field. This is an example of the results obtained. You see the valve here, and you see that there is some turbulence generating the sound waves, and here the sound waves they decay, leaving just a plain wave that you can see very well here, propagating in the duct and then radiating outside of the duct. Final comparison with the results is shown here, where you see 4 different mass flow rates. So these 4 are different mass flow rates. you can see for the frequency, the sound pressure level, dBA, so corrected for the ear sensitivity, at a given microphone outside of the duct compared with the measurements. So there is quite good matching of the experimental results. So with this, I have completed this the presentation of the some of the potentiality of VNoise for the when applied to model tonal and broadband noise, and I will give you now some minutes to maybe formulate questions if you have. So we can make a break of 5 minutes, and then if you have questions, please feel free to write down the questions, and I will give you an answer. So there is a first question asking for the previous webinar that was more a theoretical webinar, just for information of all the attenders. All the attenders will receive an email containing a link to the FTP site where they can download this webinar, and we will enclose in that FTP site also the previous webinar for your reference or for your information. So you can have both of the webinars. So there is another question asking for, in general, how to import acoustic meshes of hybrid or in VNoise. Typically, the format that we suggest to have for the importation in VNoise is the CGNS format. So from when you use a grid generator, if you can provide or output the mesh in the CGNS format, it's the best way to have a mesh imported into VNoise. And I would like to remind that this format, this mesh can be structured or unstructured, bidimensional or three-dimensional, and so it would be easy to have these the meshes imported in VNoise. Then there is a third question asking if it is possible to use VNoise for thermoacoustic application in combustion chamber of gas turbines. So I would say that the assumption made by VNoise are that the acoustic wave are linearly propagated. So the formulation that is that VNoise solves is the wave equation, the convective Helmholtz wave equation. It's a linear propagation. So wherever you have a problem or a simulation providing the results expressed in the frequency or in the time domain related to an unsteady variable like the pressure, like the velocity, and wherever you can bound your computational domain with a surface enclosing the main sources, if outside of this surface you can ensure a linear propagation, you can use VNoise. So typically you could apply a Fox-Williams Hawking surface, not rotating, enclosing inside the main sources, and in VNoise you can input the acoustic variables over this surface and then radiate these surfaces in the free field. Okay, so for the moment these are the questions received. If you have any further question, you can write to your requests to support at numeka.pe, and so at the moment I will thank you for your participation, and so don't hesitate to ask further information if you need them. Okay, so thank you to everybody.